When we speak of systems program, we are very closely tied to the hardware, and we must optimize our code to use the hardware at its maximum. So how that is done, I will show you in two ways. Okay, or I will show you the anti pattern of what gives you a bad performance over here, and also I will show you a good pattern of how caching might help you. Okay, so when we speak of any kind of a computer, the basic architecture of a computer is that you would have your RAM, okay, that is your main memory, and before that RAM, because RAM is also slower, okay, so for that you have like multiple levels of caching. Okay, so that level goes as follows. So first layer, like it is directly tied to the CPU or the ALU, that is the arithmetic and logical unit. Okay, so that is the L1 cache, which is very small in size, around like 32 KB or 64 KB. Okay, so this is the fastest. Okay, after the direct instructions on the CPU, it is the second fastest thing that exists on a computer. After that, there's L2 cache, which is also slightly slower and very small in size, like it is up to like 256 KB to 1 MB. Okay, and in fewer computers we also have something called as L3 cache. Okay, and that is a few MBs. Okay, and it is shared among all the cores. Okay, and it is slightly slower than L2 but still faster than the RAM. Okay, and after that you have your RAM. So what happens is, like if you write a code in a certain way, okay, so there's something called as locality of reference that helps your code. Okay, so that how locality of reference comes into picture. So imagine that you're using an array, say multi-dimensional array. So first we will see the bad pattern over here. So imagine a multi-dimensional array, okay, or a matrix form. In that you have rows and columns. So whenever you're running your instructions or reading or inserting data in those things, so if you go in a columnar pattern, okay, so you insert into the column and row, so like every column element you are fetching, so what happens is like that is acting like an anti-pattern. See here, so here I have written two programs, so these are identical programs. Okay, so what they do is like you have a matrix, you can say, or you could say a multi-dimensional array of 2000 by 2000 elements. Okay, so in that I am setting a predefined value of 2, and after that what I am doing is I am doing a sum of all the integers within that matrix or the multi-dimensional array. So that should give me a good comparison of what a good pattern is and a bad pattern is. So let's just run these two programs side by side so you can see how and which program performs better and which performs worse. So first we will do the bad pattern. See here, so for all this integers processing and all those things, it required 36 milliseconds. Okay, and we'll do the good pattern again. See here, this required only 3 milliseconds. Okay, so you can see the kind of difference this gives. Okay, so like you can have like multiple levels of optimization built in. Okay, so if you use the optimization flags while compilation, these results might vary even further. Okay, because when you're using a code or a pattern in such a way, like this is the bad pattern I will show you. So here what we have done is like we have used columns over here. Okay, the first iteration will be the columns here and second will be the rows. So this is the anti pattern. So you are selecting one column and your row is changing every time. So the cache lines are not in such a way. Okay, so cache lines will not be able to take the benefit of the cache. So that is why you will have something called as cache miss, and when you have lot of cache miss, then you would have something called as thrashing, which is your CPU is not performing properly or it is wasting its CPU cycles. So that is the throughput is not available for you. So this is the bad pattern. Okay, and here we have just simply taken row and column, we have switched it. Let me show you this again. See here, so this part I have kept common only, so only part is this that is changing between the two programs. Okay, so here what I've done is we have kept the row first. Okay, so rows remain constant over here and your columns are changing. Okay, so individually, so inside a single row you have all these values that you are getting. Okay, so you just have to make a mental picture of this thing. So like you are reading from an array, or you could say a box or a matrix or multi-dimensional array. So you have this row locked, okay, a single row that you have logged in, and what the CPU would do is after you do 2 to 3 insertions or like 10 insertions or reads or any kind of a thing from that, it will consider that yeah, this is the locality of reference that it has, and it will pull out all the subsequent elements in that row, okay, for further use. So that is the kind of guesswork the CPU does for you. And what happens is, like, just in case if you actually use those things, okay, then you will get the performance benefit, like we call this cache hit. Okay, and if you get a cache hit, so like if you get a cache hit over here in L1, okay, so it would be like a few nanoseconds to a fewest microseconds to the max you will get the data. Then here if you get a cache hit in like L2, then it is in a fraction of microseconds, sorry. And finally if it goes to L3 or the RAM, then it definitely goes into the millisecond scale in most of the cases. So it depends, like it could go from like microseconds to the millisecond scales depending upon what kind of program it is and how many what you call calls are made to a certain data. So this is the kind of comparative analysis that I wanted to show you. Okay, so this is how caching comes into picture and how we could use it to our advantage to get the best out of it. Okay, hopefully this would have been a good learning experience. Thank you.